Chapter 11 from Brown and LeMay. Credits. Brown and LeMay, obviously, chemistry. Also, next slide. Zumdahl chemistry. Also, next slide. I put this in here just to reference McMurray and Fay also, because I've used that in a few of the lecture notes and the work problems throughout the semester, so I wanted to get them in. So McMurray Fay is also a very good book. It's actually an excellent book. And then a lot of exposition by myself. Next slide. So these slides have been edited and enlarged upon, in some cases corrected by J.R. Goodwin, the author. Next slide. So this chapter deals with basically liquids and what happens to liquids when they boil. This is a very good lead-in into Chemistry 1412. It's leading us into the discussion of liquids and vapors, which we pick up on in Chapter 13 and 14 in Chem 1412. So the big deals here, intermolecular forces, which you've already had this, so this is going to be reviewed. The liquid state, and then vapors is going to be the new item here. So for this chapter, the Clausius-Clapeyron equation here is going to be the big deal. It's the thing that you're most likely to see probably a problem on, in addition to phase diagrams. So these last two things here, you'll want to really look at those closely. Next slide. So to just review a little bit, we already know that there are basically three states of matter, although there are some other ones that we're not going to discuss in general chemistry. Solid, liquid, and gas. So they're going in reverse order here. So over in the right, on the right side, we've got solids and then liquids and gases. And I'm going to let you look at this if you want. I'm going to go on to the next slide. Polar covalent bonds, also dipole moments we've already talked about. Let's go to the next slide. So we just need to review very briefly here. Electronegativity will increase as you go to the top right of the chart. In other words, and we don't really count this column, so as you come towards fluorine here, everything as you're moving in that direction from over here on the bottom left to the top right, it's getting bigger basically in waves. So you can kind of see this like waves coming out away from F, kind of like electromagnetic waves here. So the further you get towards the bottom left, the lower the electronegativity. And remember that we want to stick hydrogen. Hydrogen has to get moved around a lot depending on what we're talking about. So we're going to put it over like right about here, just barely above boron. So you might want to just try to remember that hydrogen is going to be about 2.1. And you may need that kind of, okay, so anyway, we're only doing this because we're going to need this to talk about polarity. Let's go to the next slide. Polar bonds are things like HCl or CH, where you have something where you have one atom bonded to another one, and one of the atoms has a stronger pull for the electrons in the bond. So it pulls the electrons towards itself, and it gets itself a kind of a partial negative charge, which we write as delta negative, the lowercase Greek delta negative. So and like this. And then the other thing is left with a little bit of a deficiency of electrons, so it's called partial positive. In this case, the chlorine, so over here, this chlorine-carbon bond is polar because the chlorine has a higher electronegativity, and you can just reference the previous slide for that and just look that up. Or you could also see, if you looked at the difference here between the carbon and the hydrogen, that's also about 0.4. Carbon, remember, as being 2.5 and hydrogen 2.1. So anyway, but the main difference here is going to be between the chlorine and the carbon. The carbon and the hydrogen difference is not that great, and actually I may have had the value for carbon wrong. It may not be what I said. It may be more like along the lines of hydrogen, so that one may not be particularly polar. But the carbon-chlorine bond is definitely polar. So there's going to be a more of a partial negative charge up on the end of the chlorine. So the way that we draw that is shown here with this arrow. You just draw an arrow pointing towards the partially negative atom, and then you put a crossbar on the bottom of it to show that's the plus end. So this bond is polar. Okay, so whenever you've got a polar bond and there's only one of them in a molecule, then the molecule here is going to be polar too, because there's nothing to cancel out this partial negative up here. So the red area shows electron density. The blue is electron deficiency. Next slide. Here's another one for ammonia. It's also polar. It has a polar bond between the 3 H's and the N. All of them are polar. So the N is more electronegative than the H's. Remember, H is about 2.1. So each of those bonds is polar, and then because they're pointing all kind of in the same direction, then the overall molecule, the whole thing, is also polar. And the way that you would figure that out would be to take what's called the vector sum. So you would just figure out what is the part of this particular dipole moment right here that's actually pointing up, and it would be maybe about that much. And then for the second one, maybe it would be about that much. And then for the third one, and these should all be equal, and then the third one would be like that much. And so when you add them all together, and so in other words, out of all of that right there, about this much right here would actually be pointing straight up. If you took the vector of it, in the direction of the y-axis. So you take the vector sum. Anyway, in this case, all of these have a vector sum that ends up giving you an overall dipole moment. Same thing over here on the right-hand side over here for water. They're both kind of pointing in the same direction. O here is more electronegative than the H's, so it pulls electrons to itself. We've talked about this before. So the molecule is polar. Let's go to the next slide. So the measure of polarity is called the dipole moment, and it's abbreviated mu, and that's the Greek letter for M, mu, the lowercase, and it's expressed in the units of debye, which if you were taking physics you'd have to worry about this, but you don't here, and it's the charge times the distance, where Q here is going to be the separated charge, and R is the distance between the two charge centers. Next slide. All right, the difference here between carbon dioxide and also tetrachloromethane, or carbon tetrachloride, the difference here is that there are dipole moments in this molecule. There's one going this way, and then there's another one that's just the same amount that's going in the opposite direction exactly. So again, O is more electronegative than C, so it's going to pull electron density to itself. So you have one dipole moment for this C and this O, and then you have another one for this C and this O, but this time they don't all point in, kind of in the same direction. They point in opposite directions. So they cancel each other out. So for the molecule as a whole, the dipole moment is going to be 0. Same thing over here. It's harder to see for this tetrachloromethane because of the way this is oriented. But remember I told you when we did VSCPR that when you have a tetrahedral shape, that those 4 different bonds are pointing in exactly the kind of direction that will cancel each other. So again, here the overall molecular dipole moment is 0, even though there's actually a dipole. For carbon tetrachloride, there's a dipole here, and then a dipole here, and then for the other two. But they cancel each other out. So overall, the molecule is nonpolar. So be sure you understand this, because this is something that shows up on the final. You can have a polar bond in a molecule and still have the molecule be nonpolar overall because they cancel each other out. Next slide. All right, so let's talk about van der Waals or van der Waals forces. In the U.S., they're called van der Waals. These first 3 things that are listed here, 1, 2, and 3, are considered to be van der Waals. These are things that are between molecules. Like if, for example, if you have water, then we're not talking about the covalent bond between the H and the O. So that would be an intramolecular bond. And we also, or at least I do, consider ionic bonds to be that way. So we're not talking about covalent bonds. We're not talking about ionic bonds here. We're talking about things that are in between the molecules, so they're much weaker. There are 4 different kinds, of which 3 are called van der Waals. The first 3 here are called van der Waals: dipole-dipole, London dispersion, and hydrogen bonds. And so we'll talk about those in turn. And then there's also something called ion-dipole forces, which we'll talk about after this. Next slide. So dipole-dipole just means you've got something like HCl, where this would be the H on this side and the Cl would be on this side. So you've got yourself a dipole here. You've got a whole bunch of them. They'll line up so that the pluses on one, or the plus on one, is adjacent to the negative on another one. The plus here is adjacent to the negative here. That's dipole-dipole forces. So they'll ask this. I mean, or I will. So they'll ask you, what do you call it when you have a bunch of dipoles that are lined up next to each other so that the forces of the positives are adjacent to the negatives? That's dipole-dipole. Next slide. And here are some examples of dipole-dipole. What you should notice here, you can look these over, but be sure that you notice this thing here at the bottom. The stronger the dipole moment is, then the more these things are going to hold each other together. And what that means in terms of something like a physical property, like the boiling point, means that it would be harder to boil the silly thing, because you have to heat it up more, because you not only have to like boil it the way you would ordinarily if they weren't polar, but you also, now you have to overcome those dipole-dipole attractions, which means that you have to heat it up more, so the boiling point will be higher than you would have expected. And that's listed down here at the bottom, so be sure you understand that. Next slide. The next kind, the second kind of van der Waals forces, called London dispersion. These are a little harder to understand maybe, but what it basically means is you can have something that's basically nonpolar, but the idea here is that at some particular moment, you might get a temporary change in the situation. Instead of where you have an even distribution of the electrons all of a sudden on one side, a little bit of the electron density for some reason will move to one side just for a moment. And it will create a very temporary partial negative on that side, which means you got a partial positive on the other side. So you got yourself a very short-lived dipole. And so if that happens, then it can cause the adjacent molecule to do the same thing. And then these things can, and it actually does happen. It sounds kind of hokey, but it actually does happen. And so what happens is you get like these attractive forces and things you wouldn't expect. Like, I mean, you might try to pick up a book that's on another book, and it's induced these dipoles, and the books stick together, and it's harder to pick the thing up than you would have expected. Next slide. Here are some more examples of this. You can pause and look at this if you want. Again, the one thing that you should notice about this is as you go from the top of this chart to the bottom, F down to I2, these are getting larger, which means there's more surface area available, which means it's easier for them to make temporary dipoles. So the dipole moments tend to go up as you go from the top to the bottom, which means they hold each other more as you go from the top to the bottom, which means the boiling points go up also. So that's another thing you should try to notice. Next slide. Also here, when you have the same molecule in two different forms, so these both have 5 carbons, but they're arranged differently. So this one's called neopentane, or at least that's the old name. This one's just pentane, which you'll study that in 1412. So what you've got yourself here is a situation where you've got way more surface area on this one than you do on this one. So that means it's much easier for the one on the left over here to have these London forces. Okay, so this one is typically going to have more London forces, which means it's going to take a higher temperature to boil it. You're going to come back to this if you take organic chemistry. Next slide. Hydrogen bonds are very important, and of the ones that we've studied, they're the ones that are the strongest, basically. Hydrogen bonds form whenever you've got a hydrogen on one molecule that can make a hydrogen bond to a lone pair on another molecule. Like you see right here, the H on the water on the right is making a hydrogen bond to the one of the lone pairs on the O on the left. Okay, so it's important to notice this little thing here that this can only happen for nitrogen, oxygen, and fluorine, or things in the second row. So in other words, this can only happen basically for H2O, NH3, or HF. Those are the only ways it can happen. And the reason for that is because when you get to the third row, the atoms are so large that they can't really make hydrogen bonds. So only things in the second row can do it, and it can only be N, O, or F, because N, O, and F are the only things in the second row that have lone pairs. Okay, so you should try to remember that. So, for example, here on this example, we have two waters. So the H on one is making a hydrogen bond, which is just an intermolecular force between those two water molecules. So that's what we mean when we say intermolecular. So notice this bond right here is not a hydrogen bond. It's a covalent bond between the O and the H. So, and that would be much, much stronger. Next slide. In water, hydrogen bonding is very important for various reasons. Whenever you have liquid water, you've got all these hydrogen bonds between the H's and the O's on adjacent molecules here. But what happens, and one of the reasons it's important is because when it freezes, they catch each other. So as you decrease the temperature and make a solid, these things would typically, like the cooler you make it, then the closer together typically these things would get, but they can't in water, whereas they can in other things, but they can't in water. The reason is because these hydrogen bonds catch and hold them in kind of a position where they just stick. Even though the temperature decreases, they just stay put. And so what happens is you wind up with a lot of air pockets in ice. That makes ice less dense, and that's different from almost everything else. And the reason, again, is because of hydrogen bonds. Next slide. Also, hydrogen bonds are important in DNA, where you have this double helix, and between them, between the two helices, you've got hydrogen bonds all the way down. So these are not real bonds. I mean, not like covalent bonds. They're just hydrogen bonds. And that's important in biology because you can actually take an enzyme called DNase, I think that's what it's called, and you can come through here and break these hydrogen bonds and unravel these two strands of DNA so that they can they can mate with messenger RNA and then send the mRNA off to make proteins and that kind of thing. And then once that's finished, then these things will just rejoin and the hydrogen bonds will recombine and you will have your DNA again. Next slide. So these hydrogen bonds can only happen in H2O, NH3, and HF. So you see here in this example that for those three things, because of the hydrogen bonds, the boiling points are higher because you have to heat it up more to overcome those hydrogen bonds. Next slide. Then the last one, which is not usually considered a van der Waals force, ion dipole forces is like if you've got yourself some water. So that would be this stuff right here. All of these would be water. They're all dipoles. And then you put NaCl in the water like salt and you mix it up. And the Na pluses break away from the Cl minuses. And then what will happen is the water molecules will do what's called solvating the ions. In other words, the partial plus ends of the waters will surround the minus charges, and the partial negative charges on the waters will surround the Na plus or whatever. So that's called an ion dipole force. It's an intermolecular force because it's not like covalent or ionic bonding, but it is not considered van der Waals. Next slide. So here's a comparison. Notice here that the ones that are the strongest out of the ones that we're calling van der Waals are the hydrogen bonds. They go up to as much as 40 kilojoules per mole, whereas the ion dipoles can actually go up to 50 kilojoules per mole. The dipole-dipole and the London dispersion forces are very weak, as you can see. And then just by way of comparison, covalent bonds can have varying strengths, but a carbon-carbon covalent bond at the bottom here can have a strength of 345 kilojoules per mole as opposed to the 50 here or the 40 here. And ionic bonds, I mean, they vary, but for KCl, you're all the way up to 427 kilojoules per mole. So these are nowhere near as strong as those, but still important, and they still have an impact. Next slide. So which are stronger molecular bonds, and what they mean by that is covalent or ionic versus inter, like the ones we just studied. We just said this, right? So the answer is clearly intra Covalent and ionic bonds are much stronger, so let's go to the next slide. So intramoleculars are going to be the ones that are more strong. I'll let you pause this if you want. Next slide. Next slide. All right, another concept check. Which molecule is capable of forming stronger intermolecular forces? So N2 can't really do much of anything, right? I mean, and it can't even really form London dispersion forces because it's not big enough, whereas H2O can form what kind of intermolecular forces? So think about it. Hydrogen bonds, right? So remember, it can only be formed when you've got N, O, or H, like water here, or NH3 or HF. Those are the only things that can form hydrogen bonds. So the answer here is going to be H2O. Next slide. Next slide. Next slide. So draw the two Lewis structures for C2H6O, or draw two of them, and then compare the boiling point. So here we have them. So the difference here, and we're comparing the boiling points, this one over here on the left can make hydrogen bonds because you've got these two lone pairs here sticking out that are accessible to make hydrogen bonds, whereas in this structure over here on the right, you can't do that because the lone pairs are hidden inside of the molecule here so that they're basically shut off from being able to make the hydrogen bonds. Certainly, if not completely, then certainly to some extent. So this structure over here, they're both the same formula, but this structure on the left will be the one that will have the higher boiling point because it can make H bonds. Next slide. And I'll let you pause that if you want. Next slide. Which gas would behave more ideally at the same conditions of pressure and temperature? So on the left, we've got a situation where we have a polar molecule because O is more electronegative than carbon. So it is not going to behave ideally because they're going to attract each other. The CO molecules will attract each other. What about the N2s? Are there any kind of intermolecular forces there? No, as we talked about before. So the N2 clearly is going to behave more ideally. Next slide. Next slide. Next. Next. So just very quickly, I'm not going to spend a lot of time on this, but you might see a definition type problem on the final especially. Viscosity means how viscous something is, and anyone who's ever bought motor oil for your car or whatever, your truck, you know that the more viscous it is, then the higher the number would be, like 1040 or just 40 weight would be more viscous than 1030. Viscosity is like, the way that you can think of this in a picture in your mind, oil is much more viscous than water. In other words, it doesn't just pour, or honey, it doesn't just pour out of the jar like water does, so it's more viscous. So viscosity is the measure of resistance to flow. Surface tension is the tension that occurs across or around the surface of a liquid where these like molecules are holding each other kind of together, and they can assume various shapes depending on where they're located. So like, for example, if you wax your car and then water gets on it, it rains, then the water will beat up, at least until the wax starts to wear off. And the reason is because of surface tension. So the surface tension of the water molecules caused by their polarity will cause them to beat up. And it also allows what's called a water strider, which is something that looks like a spider that has very long legs, can actually walk across water because it's a very lightweight and the weight is spread out over a very large surface area, and there's a certain amount of surface tension in water, so that allows it to walk across. Next slide. And here are some values for these. If you want to look at them, you can pause this. Next slide. And then very quickly, capillary action. This is the definition problem potentially. The rise of liquids up narrow tubes is called capillary action. If you've ever had your finger pricked to take a blood sample, you may remember that they just take this little capillary tube and put it where they pricked your finger, and the blood will just kind of like automatically go up. But that's called capillary action. I mean, it doesn't have to be blood. It can be any liquid. You can take a little tiny thin diameter capillary tube and put it over water or some other liquid, and it will go right up into the tube. So there's two different ways that this can happen. For things like water, you have things that are called adhesive forces, where the water will go up the wall of the tube and it will actually attract itself to the wall of the tube. Whereas in a mercury thermometer, you have cohesive forces, where the mercury attractions are actually stronger than the attractions to the walls of the capillary tube. So when you have water in a capillary tube, it's going to make, or in, like, for example, more familiar to you, like a graduated cylinder. So here's your graduated cylinder. Imagine that it goes up and down further. And if you have water in it, then it makes what's called a meniscus, because there are attractions here and here to the side of the graduated cylinder that attract the water. So the water rises up kind of on the sides. If you had the same situation, if you had the same situation in mercury, it wouldn't do that. It would go like this instead. So you have like an upside down meniscus, because these things here, these mercury atoms are drawing themselves together, and they're kind of drawing themselves away from the sides of the walls over here. So that's called cohesive. Next slide. So here we have a picture of both. See here for the water, you've got a meniscus, which you're very familiar with. On the right-hand side, you've got mercury, and you can see the difference here. It's like you took it and turned it upside down. Here's the way it looks microscopically. So these mercury atoms are holding themselves away from the side of the wall because their forces are stronger. Over on the left-hand side, this is supposed to be the left side of this meniscus. So it's supposed to be this part right here. And here's the side of the wall, and this is the water molecules, and they're kind of like going up the side of the wall. Next slide. So for mercury, which force would dominate? It's going to be cohesive. Next slide. Okay, next slide. And then for water, which would dominate? And that's going to be adhesive. Next slide. Okay, this is probably the most challenging part of the chapter, the Clausius-Clapeyron equation, but since we talked about it at the beginning of this semester, hopefully that'll make it easier for you to understand it. Let's go to the next slide. So before we talk about that, we need to talk about another review topic. When we say fusion, we're talking about melting. Solid to liquid. Freezing would be the reverse direction. Vaporization, going from liquid to gas, and sublimation is when you go directly from solid to gas. The reverse of that is called deposition, which you rarely see. Condensation means going from gas to liquid. Next slide. So on the left-hand side, you've just got sublimation and deposition, where you're going either directly from solid to gas or gas to solid. The more common scenario is on the right. So you would start off with a solid and you would melt it. So in that direction it would be called fusion, and then you would vaporize it. So in that direction it would be called the heat of vaporization, and then you can also come down in the reverse direction. Next slide. So the heat of fusion is just going to be the amount of energy that it is required to melt something, and the heat of vaporization is the heat required to, or the enthalpy required to vaporize something. And here again are some examples of this. Next slide. So here's a typical high school chemistry problem. You're going to start off with some amount of ice at some temperature, and if you want to end up with steam or vapor at a certain temperature that's above 100 degrees centigrade, assuming we're dealing here with water, then what you have to do is you have to heat the ice up to 0 degrees and then melt the ice, which the temperature won't change until all the ice melts. And then you have to heat the water after you melt all the ice. The water has to go from 0 to 100, and then you have to vaporize the water to steam. And again, the temp won't change until all the water is vaporized, and then you have to heat the steam up to whatever temperature you're trying to get to. So these are not hard problems. You just have to remember your steps. Next slide. This is just so back to the previous slide. We'll come back to that in a couple of the work problems. So we'll see some more examples of that. Next, sorry, this slide. This is an example of when you put water into a container and then put a stopper on it. And what will happen is initially you have this certain rate at which the water will evaporate at a certain temperature. But after you leave it in there for a while, you're going to have enough of atoms or molecules in the vapor phase up here that they'll start to go back down into the water phase. And at some point, the rates going up and the rates going down are going to be equal, as is shown here. Next slide. So this is just showing that the rate of the reverse thing, where it's going from the vapor to the liquid here, is going to start off slow, but eventually it'll reach a point where it's the same as the rate of evaporation that you have that's constant. And when that happens, it's called equilibrium. So equilibrium will be the dominant topic of Chem 1412. So this is like an introduction to that. Next slide. So the pressure, and this is a little hard to see. It's like when we talked about ideal gases, right? And we said that there's a pressure that the atmosphere exerts on us. And it's hard to see that because we can't see the air, and also we can't really feel it. The reason we can't feel it is because we're used to it. So vapor pressure is kind of like that. It's like, for example, if you've got a glass of water just sitting on a counter, the water in that glass is actually producing a pressure coming off the top of the water. And the pressure is coming from the fact that some of the water molecules that are in the water are evaporating. And as they evaporate, they turn into gas particles, and they exert a certain amount of pressure, just like we studied in Chapter 10. Usually it isn't very much. So like at room temperature, the vapor pressure of water is about 24 to 25 torr millimeters of mercury. It's not very much, but still it's something. It's actually there, and you do have to take account for it. So that's what we're going to be talking about here. Is we're going to talk about what happens to the vapor pressure if we have some water and we start to heat it up. What happens to the vapor pressure? So again, remember I told you a rule of thumb you might want to try to remember. It's easy to remember. Is that at 25 degrees centigrade or room temperature, the vapor pressure is about 25 millimeters of mercury or 25 torr. So if you're going to remember that, it might help you out. It may save you some time. Next slide. So, all right, here's a little question that we need to also remember this. This is different from what I just said, but we also need to remember this. What is the vapor pressure of water at 100 degrees centigrade at sea level? To put it another way, how much of a pressure would you have to heat water up to get it to boil at sea level, right? Because that's what it's asking. So what are you actually doing when you boil water? So let's just think about it for just a moment. When you boil water, you're trying to get the pressure of the water to be greater than the pressure above it. If you can do that, then the water will start to come off the liquid phase and turn into a vapor phase. So the question then becomes, what's the pressure above it? Well, at sea level, what's the atmospheric pressure? Well, it's 1 atmosphere. So try to remember this. The vapor pressure of water, if you're at 100 degrees. Now, I know I just said it was about 25 torr, but that's if you're at 25 degrees. That's at room temperature, but this is at 100 degrees. It will be about 1 atmosphere. So if you think about this, and we'll go to that in just a second. If you think about this for a minute, the vapor pressure of water went all the way from 25 torr to 760 torr, just in the context of raising the temp from 25 degrees centigrade to 100 degrees centigrade. So that's a gigantic increase. Next slide. So at sea level and at 100 degrees centigrade, the vapor pressure is 1 atmosphere or 760 torr. Next slide. I'm having a hard time again with these slides. This slide is telling us that if you have intermolecular forces, those are the ones that we talked about earlier, like hydrogen bonds and what have you, if they're large, then that means that these, for example, water molecules are going to hold each other down. They're going to resist being boiled, and their vapor pressure will actually be less. And if you want to think of it this way, like as opposed to something that was completely nonpolar, water will tend to hold itself down in the liquid state because the molecules of water attract each other. So they kind of like hold each other in place. So there isn't as much water evaporating as there would be if it were something else, something like N2, for example. So what happens is the way we say that is we say the vapor pressure is low when the intermolecular forces, like the hydrogen bonds, are large. So that means that if the vapor pressure is low, you've got to heat it up more in order to get it to boil. And then as the temperature increases, the vapor pressure, this is independent. So this thing right here is independent of the next statement. The next statement is also just a general rule that you'll sometimes see on tests. When you increase the temperature, regardless, it doesn't matter if it's polar or nonpolar, it's still going to increase the vapor pressure if you increase the temperature. Next slide. So I'll let you look at this for a second. This is just a chart showing how many molecules are going to evaporate at a particular temperature. If you have a lower temperature, you're going to have this thing moved over to the left more. At a higher temperature, you notice that this curve moves more to the right. So I'll let you look at that on your own. Next slide. And then I'll let you look at this on your own. I'll just point out that at 298, which is going to be like right here, the pressure is going to be about 25. Next slide. All right, so let's get back to what we talked about at the beginning of the semester. We have a curve on the left where we're just plotting the pressure versus the temp like we did in the last chapter, but in this case it isn't actually the pressure, it's a special kind of pressure, the vapor pressure, and that's the pressure above like water or other liquids. So we're just plotting on this side the pressure versus the temperature. In other words, as we increase the temperature as we go from left to right here, what's happening to the pressure? Well, it isn't going up in a linear fashion. It's going up like more quickly than we would have expected. And if you'll think back to what we said about water, it goes from 25 to 760 really fast. So if it were linear, it would look like this, like it would start off and it would go like that, kind of. It's hard to draw with this thing, but it isn't. It's going up like that, and we call that what we would have, if we just glanced at it, we would call that exponential behavior, because it's going up way faster than we would have expected. It turns out it isn't exactly exponential in this case, which we'll see in a minute. So what we can do is we can try plotting, instead of the vapor pressure versus the temperature, we can try plotting the logarithm of the vapor pressure versus the temperature, which I'll show you in a minute. It's not shown here, but I'll show you on a different slide. And we might expect to get a straight line, but we wouldn't. And the reason is because this is not a pure exponential, but there's no way you would know that by just looking. But the first thing to try would be to try to plot the logarithm of the vapor pressure. The thing that's going up faster here, it's going up faster in the y direction. So your y thing, take the logarithm of it instead. So take the logarithm of the vapor pressure versus the temp, which I'll show you what happens if we do that in a moment. It turns out that we actually have to do two things. We have to not only take the logarithm of the vapor pressure here, we also have to take the reciprocal of the temperature. And remember at the beginning of class I told you that taking that reciprocal is something we have to do when we have asymptotic behaviors. So evidently there's some, well, we'll talk about that in a few minutes. All right, so anyway, if it turns out that if we do that, if we plot the logarithm of the vapor pressure against 1 over the temperature, we get a straight line, which is what we're looking for, right? Let's go to the next slide. So whenever, okay, let's talk about this. So here's the original graph. So if you just take a look at this, you might say to yourself, wow, that looks exponential. So let's try plotting logarithm of vapor pressure over here and do it against temperature down here and see if it works to make a straight line. And again, as I've said several times, the reason we're trying to get this in a straight line is so that we can put it in the form y equals mx plus b, figure out what the corresponding physical characteristic is that corresponds with the m, and then we can use it to work problems. Next slide. So if we do logarithm of pressure versus temp, this is what we get. Still, it's not a straight line though. So the reason, as I said, is because there's still some different behavior in here that we called asymptotic or hyperbolic behavior. So let's go to the next slide. So as we said at the beginning of class, we get rid of that by plotting the logarithm of the vapor pressure versus 1 over the temperature. Now it's a straight line. Okay, so notice here, it's now in the form of y equals mx plus b, right? What's y? Okay, what's y? Well, y is whatever's on the y-axis, right? So it's the logarithm of the vapor pressure. What's x? Well, what's on the x-axis? 1 over the temperature. So what we're saying is that the logarithm of the vapor pressure equals m times 1 over the temperature plus b, where b is a constant that you would have to look up in a chart. So we're not really worried about the b. So the way that they rewrite this is they substitute in something for the m here. Let's go to the next slide. Oh, and I usually pull these out when I'm doing these presentations, but this one I left in because I thought it was kind of apropos. So I'll leave this up, or you can pause this if you want to look at it. I'm going to go to the next slide. So I'm going to skip over this slide where I'm just explaining to you what is meant by logarithm. Next slide. And then that brings us to this, where the key here is what we've done here is we've substituted in a physical characteristic for the m in y equals mx plus b. So we already knew what y was, right? It's just the logarithm of the vapor pressure. And we already knew what x was, and we already said that c is just a constant you look up in a chart. But it turns out that if you do a experiment on this, you can discover that the m can be replaced with the delta H of vaporization over R, the negative of that. So in other words, it's a way to relate the delta H of vaporization. What's the delta H of vaporization? It's how much heat or enthalpy is required to heat, for example, water to steam, right? So we're relating that to the m in the y equals mx plus b. And we'll do that again if you take 1412, actually more than once. Next slide. So here is actually what we've done. We've substituted m equals minus delta H of vaporization over R, and this R is going to be the 8.3141. How did we know to do that? Well, the only way they knew to do that is they did a bunch of experiments and tried to find something that's like an actual physical characteristic that they can substitute in for the m, because that's something that seems to happen a lot. So they just kept playing around with it, and they finally discovered that the thing that actually would fit in here and that actually works and corresponds is the heat of vaporization, which is kind of logical, right? It might be one of the first things you would look at, because the heat of vaporization is definitely related to the relationship between vapor pressure and the temperature, right? So they probably started with that and just played around with it until they figured out that to get it to work exactly right, you have to divide it by R. So what that means is if you can get a plot of the logarithm of the vapor pressure versus 1 over the temperature, find the slope, then you could figure out what delta H of vaporization is by taking the negative of that number divided by, or multiplied actually, by 8.314 joules per mole K. So that would be a kind of problem that you could be asked. And I think, actually, I've seen that asked on an exam, a final exam, maybe one time. So as I recall, like when I first started teaching, the departments usually put out the finals, not us. And there was a question where they gave you, either they gave you a graph and you had to find the slope yourself, or they just told you what the slope was. And then you had to figure out what delta H of vaporization is. And you can just use that equation at the top. M equals minus delta H of vaporization over R. And figure it out if you know what M is, right? Because you know what R is, and you've got 3 things there and you know 2 of them, then you can figure out the third one. So don't panic if you get that or something like a derivative of that on the final exam. Just take your time and recall what M stands for. And if they don't have it written like this, which they undoubtedly won't, all you have to do is look at your formula sheet, find the Clausius-Clapeyron equation here, which will be on there, and then look to see what's in front of the 1 over t. Well, it's minus delta H over R, right? So that's going to be the thing that equals the M. In other words, these 2 things right here are interchangeable. All right, so anyway, back to what the main focus here. This is one way that you can write this so-called Clausius-Clapeyron equation. And then there's another, and you occasionally will see problems like this where they'll give you like everything except the vapor pressure. So they'll give you the delta H, and of course R is always 8.314, and they'll give you the temp, and they'll give you the C. or they'll give you a little chart to look it up. And then you just solve it, just like any other equation. Solve it for logarithm of p first, and then convert that to p. But I think it's more common to see this in a different form. And the different form, and this requires a little explanation, the different form is where you do this at one temperature and find the vapor pressure, and do it at second temperature and find the vapor pressure. And so what happens is you can do it at, let's say, T1 and T2 and get P1 and P2. And then what you can do is a little mathematical trick where you just subtract what you got at 1 minus what you got at 2. Or you could do it 2 minus 1, it doesn't matter. And when you do that, mathematically, that C over there on the right-hand side, this C right here, goes away because you're getting C minus C, and that's just 0. So you end up with a relationship where you got logarithm of P1 minus logarithm of P2, or the reverse of that, equals the delta H over R, and then it's actually, I think it ends up being 1 over T2, and we'll see that in just a minute, minus 1 over T1. In other words, you're just making up a new equation. So this equation is a stationary problem type equation like we saw in Chapter 10. And the other one is going to be like a before-after, where you've got two different temps. Next slide. So without going through a long talk about this for the sake of time, this is the way that you end up with that second kind of equation that I spoke about. This is what you would actually end up with. So you get logarithm of P1 over P2, which you can also write as the logarithm of P1 minus the logarithm of P2. This is just a logarithm rule, equals delta H of vaporization over R, and then it's multiplied by 1 over T2 minus 1 over T1. Now again, as always, when you're dealing with these 1 over things, these reciprocals, you always have to be real careful when you're doing these. Like, I mean, if I were you, even though you don't have to do this, I would write out on a piece of paper what 1 over T1 and 1 over T2 are, assuming you have T1 and T2 provided, because it's so easy to screw these up. Okay, anyway, let's go to the next slide. So here is a problem. The vapor pressure of water at 25 degrees centigrade is about 24 torr, and the heat of vaporization at 25 degrees. And I should point out here that the heat of vaporization changes with temperature. But we're going to consider in this class and in 1412 that it's constant, that it isn't a function of temperature. But when you get into physical chemistry, that's one of the things that you do in more advanced chemistry classes, is you say, oh, okay, but really we were simplifying things in general chemistry, but now we're going to see how they really work. But don't worry about that for right now. But anyway, the heat of vaporization of water is 43.9 kilojoules per mole, and we know what R is already. Calculate the vapor pressure at 65. So is this a before-after problem, or is it a stationary problem? Well, it's a before-after, because they gave us an initial temperature, 25 degrees centigrade, and a final temperature of 65 degrees centigrade. Don't forget, these have to be absolute temperatures. You can't write 25 and 65. You'll get the answer wrong. You have to write 273 plus 25, which is 298, and then you have to write 273 plus 65, whatever. I think it's 338, but whatever it is. And then which formula would we use? The first one, or no, we'd use the second one, right? We need the one that has P1, P2, and T1, T2. So just go back to the previous slide. That's the formula that we would need. So let's go to the next slide and look at that. So here's our formula, and it's written in a little bit different form, but it's the same formula. So logarithm of P1 over P2 equals delta H of vaporization, 1 over T2 minus 1 over T1. So what's given to us? Well, both the temperatures are given. So the first temperature is 25. The second temperature, T2, is going to be 65, added to 273. So that was given. R we already know. Delta H of vaporization was given as 43,900 joules per mole, where I've converted it to joules because the other things are going to be in joules. And then we know one of the P's. We know that P1 is 23.8 torr. We can leave the P1 and P2 in torr because we just need the ratio. And we just need, so first of all, let's find this whole thing. Let's find the whole quantity on the left-hand side by just substituting in what each one of these things on the right is. So T1 is going to be 298, T2 is going to be 338, R is going to be 8.314, delta H of vaporization is going to be 43,900 joules per mole. So just go ahead and do the math there. Again, be careful with your reciprocals. And that will tell us what the logarithm term over here on the left is. And it turns out that that is minus 2.096. So just be sure you do that on your own, just to make sure that you know how to do it. And then to get rid of the logarithm, as always, we raise both sides of the entire equation to e to the power of. And that gives us 23.8 torr divided by P2 equals e to the minus 2.096, which that turns out to be 0.122. But we know what P1 is. It's 23.8 torr. So we can just solve then for P2 by using this equation right here at the bottom. Where did the 23.8 come from? It was given in the problem statement as the first pressure at the original temperature, okay? So just solve that one for P2 and you get that P2 is 194 torr. And this is the most likely way that you're going to see this on my exam and on the final. You might also see, mainly on my exam, a stationary problem where you would use that first formula that we did that didn't compare T1 to T2 and all that. Next slide. All right, I'm going to try to wrap this up in the next few minutes because I want to try to keep this under an hour. Which would you predict would be larger for a given substance? So let's just take water, because it doesn't matter because they didn't tell us anything specific. Would it take more heat to melt ice, or would it take more heat to boil water? And if you didn't already know, the answer is it takes a lot more heat or enthalpy to boil water. A lot more. So the delta H of vaporization is going to be the larger quantity by far. Next slide. Next slide. Next slide. As intermolecular forces increase, so in other words, as the forces between the atoms or the molecules gets larger, what happens to each of these? Boiling point, and then viscosity, surface tension, enthalpy of fusion, freezing point, vapor pressure, heat of vaporization. Okay, so let's just go through these one at a time. Boiling point and freezing point are going to go up. Boiling point and freezing point both go up because it's harder to boil it or melt it, because the atoms or molecules are holding on to each other more. Viscosity goes up also because as you increase the forces, they hold each other together. Same thing for surface tension. Both of the thickness of it and also the amount of tension that's on the surface will increase because they're holding each other together more. And we've already talked about, no we haven't, enthalpy of fusion, the amount of heat it takes to melt it will go up also. So, and then the heat of vaporization also will go up. So the enthalpy of fusion is how much heat does it take to melt it. The heat of vaporization, how much heat does it take to boil it. So those will both go up because it's harder to melt it, it's harder to boil it. The vapor pressure is the only thing that will go down. And the reason is because as these things hold each other down in the solution or the liquid, then it's harder for individual atoms or molecules to escape, which means the pressure of the escaping gas is less. So all of these are going to go up except one. Can you remember which one that was? It was the vapor pressure, and that's because the vapor pressure, the pressure that's above the liquid will go down because it's harder for things to evaporate. Next slide. So here are your answers if you want to pause and look at that. Next slide. Phase diagrams, let's try to get through this. So phase diagrams next are the things that you're most likely to see on the final, and you'll see them also in my exam. So let's go to the next slide. It's easier just to look at them. So phase diagrams are plotting the pressure of a system versus the temperature. So now we're not just talking about vapor pressures here, we're talking about pressure period. So we're actually talking about not only the liquids and the gases here as we were before, but now we're adding in solids. Okay, so first of all, look at the general structure here. What you need to try to remember here is that you've got three different phases, right? We've got solid, liquid, and gas. You need to remember how they're in here. The only way that you can put three different phases in is to put the one in the middle that can turn into the other two. In this case, it's liquid, because the liquid can boil and make gas, or it can freeze and make solid. If you put the solid in the middle, How are you going to put all three of them on here? You can't. But the reason I'm saying that is because you have to remember that, because what they'll do is they'll give you one of these that doesn't have anything written on it. It'll just have the lines. So the first thing you need to remember is which one of the ones is in the middle, solid, liquid, or gas. It's going to be the liquid. All right, so the next thing you need to remember about this is that at some point all three of these things are going to meet in one point, and that here for this stuff, which we're doing water here, is right here, and that's called the triple point, and they'll always ask that. So when they ask you what's the triple point, look for the place where solid, liquid, and gas all come together in one spot. And then there's always going to be another spot up here, right here, called the critical point. That's another thing they'll always ask. And that's a very unusual thing that you probably never heard of before. Most people haven't. And it turns out that at some temperature, if you keep heating up a system like this, like water, if you keep heating it up long enough, if you get it hot enough, it will reach a point where it will turn into something that's like not really steam or water. It's like a completely new thing that's called a supercritical fluid. And I'll let you read a slide that I put in here if you want. You can pause in a minute. But this is something that most people aren't even aware of. And you can also get to the supercritical fluid by increasing the pressure. So whether you increase the pressure to a certain point or the temp to a certain point, you still wind up with this stuff called the supercritical fluid. So the temperature that you have to get to for water to get that is 374 degrees centigrade, which is called the critical temperature. And the critical pressure is about 218 atmospheres, which that's a huge pressure. So the pressure at which you reach the supercritical fluid would be at 218 atmospheres, because that's called the critical pressure. This line right here, and I'll try to approximate it, is the line that separates between liquid and gas. So when you're exactly on this line, that means that if you wanted to go a little bit in this direction, you're going to have a gas. If you want to go in this direction a little bit, you wind up with a liquid. Same thing here. This line right here is separating between a solid and a liquid, and this line right here is, what is it separating? Is this also liquid gas? No, it's solid and gas. So if you go from this point right here to this point right here, you're going in the direction of what we call sublimation. You're going directly from solid to gas. Now, the one other thing we really need to notice here, because it's going to show up on exams, is that this line right here between the solid and the liquid is going off to the left. In other words, it's decreasing. It isn't going straight up. And everything, just about everything else, or almost everything else, doesn't do that. Almost everything else goes this way, as we'll see in a minute. So why is water different? Well, think back to what we said before. What happens when water freezes? In other words, goes from a liquid to a solid. Well, the hydrogen bonds get in the way, right? So they create spaces, and they wind up making the solid less dense. So the way that this is usually phrased on an exam would be that what would happen if you started off, for example, right here, and you increase the pressure and keep the temperature constant? And again, it's hard to draw with this. What happens if you increase the pressure? Well, what happens? Well, what did we do? We moved, and you may not be able to see it very well from my crappy drawing, but we moved from the solid to the liquid. In other words, we melted the ice by increasing the pressure. Now, if you've ever lived in a place like Minnesota, as I have, then you may realize that one of the ways you can melt ice is just by either walking on it a lot or driving a car over it, at least in some circumstances, like especially when the temperature's not real cold. Because what you're actually doing is this: you're actually breaking those air cavities, and you're putting pressure on that ice, and you're like smashing those hydrogen bonds and removing those air cavities and making that solid more dense, which under the right conditions can actually cause it to melt. So that's what we're seeing here, and this, again, this is unusual. But let me try to draw this again. We're starting off at a point like this. We're not heating it up, and yet we're still going to be able to melt it by raising the pressure. So we're causing it to go from a solid to a liquid by breaking the hydrogen bonds, and we're just basically liquefying it. All right, let's go to the next slide. I'm going to have to finish this. But let's just, this is water again. I'll let you look at this on your own. Let's go to the next slide. A few definitions here. Okay, but we've already talked about these, so let's go to the next slide. I need to get done. And this is the slide that I told you that I would let you look at if you want to. You can pause where it talks about the supercritical fluid. Let's go to the next slide. And then we'll finish here, I think, with this. Yeah, so, and we're right at 1 hour, which that was actually my goal. So notice here, this is not water. This is carbon dioxide. And so if you look here, notice that this line right here isn't going the way it did for water. It isn't going that way. So you can't do, for example, for dry ice, which is solid carbon dioxide, you can't do what we just did. You can't start here at a certain temperature and increase the pressure and melt it. And that's typical of most things, and water is an exception. So you need to remember that, because they always ask this on the final exam in some form. So if they told you that you started at a certain temperature, increased the pressure dramatically, and it stayed as a solid, and it started as a solid, then what would the phase diagram look like? Well, you'd know that this line right here has to be pointing up and to the right, not the way it was for water, where it was pointing up and to the left. Okay, so remember these things. Remember, the liquid goes in the middle, the solid goes on the left, and the gas goes on the right. I mean, I suppose you could do it the other way, but nobody ever does it. So just remember it that way. This point right here is the critical point. This fluid up here is called supercritical fluid. Just, you'll have to memorize these. It's not hard. This is the triple point, and I didn't see this when I made these up, but this is pointing in the wrong place. It should be pointing right here. So my apologies for that. Okay, this is going to be the critical pressure. I'm sorry, this is going to be the critical temperature. My bad. And this is going to be the critical pressure. This is going to be the triple point right here. And then this line right here is going to be the line that separates between solid and gas. All right, so that wraps it up. So for all kinds of different reasons, let's go ahead and close this. And this is also our last chapter. So I'll see you in the work problems, and whenever you get to them, and just wrap the whole course up.